Hi everyone. So today we're going to begin our study, our deeper dive into quadratic functions. And just like linear functions, quadratic functions have three different forms. Actually, there's more than that, but three different forms that we're going to look at that are equivalent. They're just written differently. So I want you to think linear functions for a second. We have point slope, we have slope intercept, and we have standard form. So with quadratics, we have the same thing. And so each one is going to give us really cool information that we're going to be able to do something with. So you actually are pretty familiar with some of them. Actually, all of them. You probably just never really thought about it. So standard form of a quadratic function is going to be of the form y equals ax squared plus bx plus c. Okay? And, you might see it like this, like y equals, x squared plus 6x plus 9. So a, b, and c are coefficients. What's really interesting about this one, and we're going to dive into that, is if I ask you to find the y-intercept, remember to find the y-intercept, you let x be 0. So if we let x equal 0, this would become 0, this would become 0. So c would always be the value you get on the output of that. So when we're looking at a quadratic in standard form, we actually can see the y-intercept just by looking at it. Now, A also can tell me some more about the graph. Remember, we learned about A telling us if it opens up or down. And so if A is greater than 0, it's going to open up. And if A is less than 0, it's going to open down. Okay, but for now, that's all you need to know is really just the form. I want you to get used to seeing the form. We've been working the last couple of weeks with a vertex form. That's where we translate the graph. Well, it's really going to be of this form, y equals a, x minus h squared plus k. Okay, and you've learned through those translations that hk is the vertex, which is why we call it vertex form, because we can see the vertex just by looking at it. And again, A still tells me it opens up or it opens down. The last one I'm going to formalize right now, but you actually probably don't really have it as a formal vocabulary word in your toolbox. So if I were to take standard form and factor it, that's actually when we get intercept form. And if it were me, I would call it X-Intercept form. Okay, and that's going to look like this. Y equals a, x minus p, x minus q. So look, it's in factored form. So we could also, if we really wanted to, we could call it factored form. I sometimes call it that. Now, you can see that if we were to set this equal to 0 and solve it, then p, comma 0 and q, comma 0 would actually provide me with the x-intercepts of the graph. Okay, so again, you might now see why I'm calling it x-intercept form. Okay, so these are the three forms we're going to be looking at. We're going to look at each one in detail, and we're going to look at really specifically what they provide, which one's easier, how do we solve them, what are all the things we can do with them. All right, let's talk a little bit more about some of the features of the quadratic graph. So we know that the graph of a quadratic is called a parabola. We've spent some time on it, but we're going to dive deeper. So we got to really make sure we understand a couple of things. There are some key features of this graph. So this graph has a point down here. We call it the vertex. So I'm going to label that. Okay, and the vertex basically, if the graph opens up, then the graph's going to have a minimum value at that vertex. And if it opens down, maybe in this direction, it's going to have a maximum. Okay? We can find all those things with our calculator. It also can have x-intercepts, right? So you can see here, these are our x-intercepts, where it crosses the x-axis. Now, when we're talking about this function, we call x-intercepts with actually all polynomials. We call them the roots. We call them the solutions. We call them the zeros. And some of those then become X-intercepts for us. So those are kind of synonyms that we kind of have to know. Now, what's interesting is I want to make sure you kind of understand this. I'll sketch it over here. It doesn't have to have two X-intercepts. A parabola can actually touch the graph just one time, like right there, where the vertex actually is the X-intercept, and it can actually not cross the X-intercept, the X-axis at all. This is when we have something called imaginary roots or imaginary zeros, and we're going to be talking about that later in this unit. Okay, then it's really important to notice that there's symmetry to the graph. So there's a line that goes right down the graph, and we call that line an axis of symmetry. Axis of symmetry. And we will write its equation, and you should be noticing it's a vertical line, so we'll always take on the form x equals some number, the axis of symmetry. But what does it do? Well, it behaves like a mirror for us. So for example, here's the y-intercept, right, on the y-axis. If I see that mirror, I can see that there's a reflection point right across it. And there is everywhere around it. Look, I can see all these points, they reflect. They're the same distance to that point. And if you really think about that, what does that mean? That anything on the axis of symmetry, how far it is away from the sides of the parabola? Well, it's the midpoint. So the x coordinate here, because there's a vertex xy, is always going to be the midpoint between any of the two reflection points on a parabola, which is kind of cool. Okay. All right, the domain, I'm sure you remember now at this point, is negative infinity, comma, infinity. And the range, basically, it relates to the y coordinate of the vertex, right? So it's either going to be negative infinity, comma, y, or y, comma, infinity. So this is going to be if it opens up, and this one's going to be if it opens down. All right, so really that is just an intro, a little taste of quadratics, and we're going to go, we're going to dive really deep into that in the coming weeks, and we want you to feel really, really good about this topic. All right, have a great night.